Okay, so welcome to chapter 5. And 5.1, all of chapter 5 is going to be solving systems of linear equations by graphing. All of chapter 5 is going to be solving systems. We best get some definitions of what a system is. So here we go. A system of linear equations. So what we're going to be dealing with are lines. Linear equations are lines. It's what we've been dealing with all of chapter 4. A system of linear equations is a set of two or more linear equations, two or more linear equations with the same variables. And if you think back to a linear equation, most of what we have been dealing with is x and y. And that's the majority we're going to see here till we get to real life problems, is linear equations. They will look like y equals mx plus b, or we are going to make those equations look like y equals mx plus b. So two or more equations makes up a system. And what we are going to do is find solutions to those systems. A solution of a system of linear equations is an ordered pair. It's an ordered pair. You are going to have an x and you are going to have a y. A solution of a system of linear equations is an ordered pair that is a solution of each equation in the system. And more specifically, it is where the lines intersect. So before we get in to solving by graphing, we're going to take a look at what a solution is. Now remember, and we have been doing this all along, if I said, hey, let's solve this equation right here, x plus 3 is equal to 5, and let's say you went through all the steps, one simple step here, and I know this could be more complex, but it'll work for our example. 5 minus 3 is 2. And you got x equals 2, and you raised your hand and said, Mr. DeLong, is that answer right? I'd say, I don't know. You tell me. How would you tell if this is a solution to that equation? Hopefully you would tell me, and I've told you enough, that I can certainly check that in there. I can take that x and plug that back in. 2 plus 3, does that equal 5? Well, 2 plus 3 is 5. 5 certainly equals 5. I checked it. It's a solution. It gives me a true statement when I plug it back in. Remember, ordered pairs that lie on a line are solutions. These ordered pairs, when plugged into the equation, let's say this is y equals 2x plus 1. They are solutions if these xy ordered pairs can be substituted into the equation and give me this true statement up here. So if I said, let's see, if I said this is the ordered pair 2, 3, and the question is, does the ordered pair 2, 3 lie on the line? Well, yeah, it looks like it lies on the line, but is this the equation? I would just take my x and my y and substitute it in. 3, does that equal 2? Actually, let's switch this. I'm going to make this 1 because I want to prove that it does lie on the line. I take my y and I substitute it in there. I take my x and I substitute it in there. So that would be 2 times 1 plus 1. 3 is equal to 2 plus 1. 3 then is equal to 3. It would check, and I know that that point lies on the line. When you're dealing with a system, you are dealing with two linear equations, and you are dealing with the intersection of those lines. Actually, I can leave it like this. I'll just pull this up. I have a system of linear equations. I've got, let's say, this equation right here, or this line that's rising with positive slope, and this line that is falling. And remember, we have an infinite number of points that lie on each line. What we are doing with a system, and when we solve by graphing, we are going to put these in a coordinate plane. And this point right here, right in the middle, where they cross, where they intersect, that ordered pair right there lies on both lines. It is the only ordered pair that if I plugged it into both equations that were given, let's say this is my y equals 2x plus 1, and let's say this is y is equal to negative x plus 2 or something like that. It's got negative slope. Doesn't matter what the equation is. What matters is that if I get this xy ordered pair and I substitute it in both equations, if it gives me true statements for both of them, I know that it lies on both lines. And the only way a point can lie on both lines is if it is where they cross. If I chose any other point on any other line, I took this and plugged it into both equations. This point right here, it would certainly give me a true statement for this one, but it ain't for this one, because it doesn't lie on both lines, and the only spot that happens is where they intersect. That is what we are doing. We are going to graph two equations in one coordinate plane. The solution to the system is the ordered pair of the intersection. And because it's an intersection, it lies on both lines, and it will be solutions to both linear equations. So that's what we're doing. So we'll go back to our notes right here, and we're just going to do a solve by graphing. And there's certain steps that we're going to use. So this is solve by graphing, and this is what's going to be in the assignment and what we're going to be working on. Solving systems by graphing, I should say, but that's okay. There are certain steps that you are going to follow. Little roadmap here. Step 1. Solve for y. We've been doing this for 3 chapters now. We want to make sure that these equations look like y equals mx plus b, because that's going to be our go-to to graph them. Get it solved for y so we can graph them. I mean, you could certainly use intercept form. You got to get them graphed. But our go-to for most of us is going to be to get it to y equals mx plus b. Step 2. Once we have y by itself, you need to graph each equation, and we're going to be dealing with systems with 2 equations. Graph each equation in the same coordinate plane. And they have to be in the same coordinate plane, because if they're not going to intersect. So one coordinate plane, both lines looking for the intersection, where they cross. Step 3, once you have them graphed, we will estimate, hopefully it's right on the money, but we will estimate the point of intersection. We're going to see where those cross. And the last thing that we are going to have to do is what we did on the sheet of paper right before this. We are going to have to check that ordered pair of the intersection. So I will say check the point from step 3 by substituting your x and y, your ordered pair, into each original equation. So you're going to have to do it for both of them. And we got to do it for both of them because in order to be a solution for both of them, it has to lie on both lines. And we just discussed, in order for it to lie on both lines, it has to intercept. So here's our example. Our directions are going to be to solve by graphing. And these are what the 9 problems you were going to work on for the rest of the week, or how many ever I decide to give you. This is the way they're going to go. So here's a system. I've got the linear equation y equals 2x plus 5. And y is equal to negative 4x subtract 1. And accuracy is going to be key here. We can't be freehanding our lines in. We can't be making a graph that's off scale. It has to be precise because I need to get that exact intersection. If it's a little bit off, it might be true for one equation but not the other. And we want to make sure that we get the solution that is good for both of them, and the accuracy will be key. So I'm just going to follow my steps to do this. Solve for y. Ask yourself, does it look like y equals mx plus b? If it does not, make it look like y equals mx plus b. Look at these. Do they look like y equals mx plus b? They do. This is going back to 4.2. Once it looks like y equals mx plus b, the easiest way to graph is going to be to identify my slope, or my m. I have a slope in the first equation of 2 over 1. A rise of 2, a run of 1. It's going to have positive slope, it's going to increase, and it's going to cross the y-axis at 5. My y-intercept, or my b, is 5. In equation 2, my slope is negative 4. And I'm going to just put negative 4 over 1. And my b, or my y-intercept, is negative 1. Step 2, graph each equation in the same coordinate plane. Well, I best make a little coordinate plane here. and I certainly want to be accurate with it. So I'm going to take some care in making an accurate coordinate plane. On your homework, sometimes you will have graphs, sometimes you will not. Sometimes we will have to construct them, sometimes I will give them to you. Remember, this is my y, this is my x-axis, and now I'm ready to graph these. Back to y equals mx plus b. Once you have identified your slope and your y-intercept, if you look back at your notes, the first step said plot the y-intercept. It's at 5. Here's my y-axis. I go up to 5. 1, 2, 3, 4, 5. And I place my point. I leave my pencil right on that y-intercept of 5. And then I have a rise of 2, a run of 1. Up 2. That's off a little bit. Up 2 to the right 1. Up 2 to the right 1. And it gives me positive slope, and it should because 2 and 1 are both positive. And from there I can get subsequent points on the line. And because I am definitely wanting to be accurate, I am going to definitely make more than 2 points to make a line. Because if I connect these, and my ruler's just a little bit off, I'm hitting this and this one, but it's going to get away from this point at the top. You want to have as many points as possible to line those up so it's as accurate as possible. This line doesn't stop at the y-axis, remember. It also comes down in this direction. It's linear, it has a constant rate of change. So I can also go down 2 and to the left 1. And remember, if I go down 2, that's negative, and to the left 1, that's negative. Down is negative on the y, to the left is negative on the x. So if I have negative 2 over negative 1, I'm just going down 2 to the left 1, and that's what carries this line back. And I'll just keep carrying it back, going down 2 over 1, and now I have several points that will make this line nice and accurate. Boom. I'll throw some arrows on it, and I have my first line. My second line has a slope of negative 4. It's going to fall, and it has a y-intercept of negative 1. I go to the origin. Negative 1 on the y-axis is right there. And now you are going down 4, 1, 2, 3, 4, to the right 1. Because remember, this is negative 4 over 1. But it could also be 4 over negative 1. That's still, negative 4 divided by 1 is still negative 4. 4 divided by 1 is still negative 4. So I can also go up 1, 2, 3, 4 over 1. I get that point right there. 1, 2, 3, 4 over 1. Now I'm not going to need to be as accurate on this one because I got a precise intersection there using my slope in both equations. I will connect those lines. Taking care to line it up just to make sure it looks good. And remember, I am looking for the solution of this system, which means I am looking for the intersection. Solutions of systems of linear equations are ordered pairs. I need to know what that ordered pair is because that ordered pair is going to be the solution. It is going to tell me where these lines cross. It is going to be the point that lies on both lines. This is the ordered pair. To the left 1, so negative 1, up 3. That is step 3. I just estimated the point of intersection. And I've got it. And I'm pretty sure on that one because I was really accurate. But I can't be positive. You are always going to have to show step 4, which is your check. And to check, we check just like we check any equation, except now we've got 2 variables, an x and a y. Remember, we're using y equals mx plus b. So in my first equation, I have y is equal to 2x plus 5 and I have this xy ordered pair of negative 1, 3. You have an x, you have a y. The y gets substituted in for the y, the x for the x. Do you have to show this? Yes, you do. It's the way to prove that you get it right. If you do this, you can't go wrong. You will always get the right intersection. So 3 would equal 2 times negative 1 plus 5. 3 would equal 2 times negative 1. Gives me negative 2 plus 5. Negative 2 plus 5 is 3. 3 equals 3. That one checks. I got to do the same thing for my other equation. Now my equation, though, is y is equal to negative 4x minus 1. And I simply still just plug these in. 3 is going to go in for y, and 1, negative 1, will go in for x. 3 then is equal to, well, negative times a negative is a positive. Negative 4 times negative 1. Positive 4, subtract 1. 3 is equal to 3. It checks in both equations, and I will box in my solution of negative 1, 3. And that is how we solve systems of linear equations by graphing. We get the intersection, and then we test the point and prove it.